On the afternoon of April 17th, a remarkable and violent display of atmospheric power unfolded across the American Midwest, generating 54 tornadoes in a matter of hours. Two of these storms, classified as powerful EF3 SES, were so intense they erased entire neighborhoods in Wisconsin in less than 90 seconds. Yet, the most unsettling detail of this event is the proposition that none of it was random. Every storm, every siren, and every damaged home materialized exactly where a peer-reviewed study from 2015 had indicated it would. This suggests our atmosphere is following a predictable path, as if turning pages in a script written by its own physics. Later this week, it seems the next page will turn, as a single weather system is projected to unleash a rare combination of tornadoes, blizzards, wildfires, and floods on the same day. All of this is occurring before the official arrival of El Nino, which raises a critical question. If this is merely the prelude, what should we expect when the main event truly begins? We invite you to join the Calm Space community to follow these developments. We are curious to hear your own reflections on these patterns, wherever you may be watching from. If the atmosphere is already adhering to a scientific playbook from 2015, delivering such extreme weather on a consistent 6 to 8 day cycle, how much more intense might these events become once the Pacific Ocean fully commits to its El Nino phase? The events of April 17th were not a chaotic anomaly. In a way, they appeared to be scheduled. Across a single afternoon and evening, 54 tornado reports were filed, with 28 later confirmed as having touched down. 2 of these were rated EF3, placing them in the top 2 to 3% of all tornadoes recorded in a typical year. Within these 2 storms, winds surged past 136 miles per hour. In Ringgold, Wisconsin, and throughout Marathon County, entire neighborhoods were reduced to splinters and insulation. Homes that had stood for generations vanished in under 90 seconds. The force was immense, tossing cars and snapping trees that had been rooted since before the Second World War as if they were dry twigs. It's a stark reminder of the immense power hidden within our skies. Over that same 2-4 hour period, the sheer scale of the event becomes even clearer. The Storm Prediction Center documented approximately 750 total severe weather reports. More than 300 severe thunderstorm warnings were issued, alongside over 150 tornado warnings that broadcast urgent alerts through phones, televisions, and weather radios. To place these figures in context, a comparison to a normal April day is almost impossible. The scale of this outbreak stands alone, occupying a space where no direct comparison exists. Despite this incredible intensity, the number of casualties was astonishingly low. This single detail should not be overlooked, as it offers the most important clue to understanding what truly happened. The low casualty count is a testament to the effectiveness of modern forecasting and warning systems. When a weather system of that magnitude moves through populated areas and flattens neighborhoods, a significant human toll is often expected. The fact that warning systems performed with near-perfect accuracy, that people sought shelter, and that forecasters had identified the threat hours in advance reveals something profound. It tells us that the atmosphere on April 17th was behaving not with randomness, but with a profound and unsettling predictability. This predictability is the thread that connects everything. The 2026 tornado season is not being depicted as lawless or chaotic, but as a highly structured pattern, driven by the El Nino Southern Oscillation. It is unfolding almost exactly as a scientific study predicted it would more than a decade ago. The real question, then, is not what happened on April 17th, but what will happen when the forces driving this pattern grow even stronger. Just 6 days later, the atmosphere appears to be reloading. This phrasing is chosen with care, as the system is not resetting or calming down, but preparing for another cycle. The same atmospheric machinery that produced the April 17th outbreak is spinning up once more. For days, the Storm Prediction Center has been signaling this, outlining a 15% risk area across the plains and Midwest for April 23rd. This risk assessment is not a guess. It is the product of models observing the exact same atmospheric configuration, reassembling over the Rockies, like a stage crew, methodically resetting the scene between acts of a play. This means that the forces that generated the April 17th outbreak never truly departed. They merely paused. The essential ingredients, the moisture, the wind shear, the instability, the jet stream positioning, and the upper-level trough, are all reconstituting. It is the same recipe, from the same kitchen, with the same chef. This is why the assertion that this is not isolated severe weather is not a dramatic overstatement, but a precise observation. This is a repeating atmospheric configuration. When such repetition occurs with this level of fidelity, the phenomenon ceases to be mere weather and becomes what scientists call a pattern. Typically, a tornado season unfolds as a messy, disjointed series of events with no discernible rhythm. An outbreak might occur 1 week in Oklahoma, followed by another 3 weeks later in Mississippi, and then a month of complete quiet. In a normal season, the ingredients for severe storms come together almost by accident. When they do, storms form. When they do not, the skies remain calm. This is the chaotic, inconsistent, and difficult to forecast nature that usually defines the month of April. The season of 2026, however, presents a starkly different picture. It appears structured. The outbreaks are arriving on a predictable schedule. The geographic areas being affected remain consistent. The atmospheric ingredients are appearing on cue, with the parameters for severe weather repeating themselves with an almost eerie similarity from one event to the next. When all this data is laid out on a calendar and a map, what emerges does not feel like a weather season at all. It feels like a system that is being actively driven by a larger force. And it is within this structure that a sense of unease begins to surface. If this season is predictable, if it is following a set of rules dictated by the state of the Pacific Ocean, and if the atmosphere is behaving exactly as theory suggests it should, then the April 17th outbreak was not a surprise. It was a confirmation. By extension, the event now forming for April 23rd is not a coincidence. It is simply the next line in a script that was written years ago, now being read aloud in real time across the sky. This early predictability, with the Pacific only just drifting towards full El Niño conditions, raises a profound question about the outbreaks yet to come. If the atmosphere is already performing this way during what is essentially a warm-up, it suggests that the main event, whenever it arrives, will be something that demands our most serious attention. The key to understanding what is unfolding lies not within the storms themselves, but in the behavior of the larger system after the storms passed. Because in truth, the event never concluded. The system did not end. It is, in fact, still active. Our typical mental model of a tornado outbreak is one of a discrete event. It arrives, inflicts its damage, and then it departs. The following morning, the sun emerges, cleanup efforts begin, and the atmosphere resets for whatever comes next. For most tornado seasons, this is a reasonable framework, but it does not apply to this one. The system that struck on April 17th never fully dissipated. Days later, its influence remains imprinted upon the landscape. The atmosphere that spawned it has refused to do what a normal atmosphere should after a major outbreak. It has refused to reset. The story continues to be told by the region's rivers. Across large portions of Wisconsin and Kansas, flood warnings remain active because the immense volume of rain that fell with the tornadoes did not drain away in a single afternoon. It is still navigating the drainage systems, causing water levels to rise in some areas and threatening towns that believed the danger had passed when the funnel clouds receded. This is not a detail one typically observes after a spring outbreak. Usually, the hydrological signature diminishes within a day or two. This one is not fading, it is lingering, a clear sign that the atmospheric engine that delivered all that water has not moved on. This is the essence of what it means for the atmosphere to fail its reset. In a typical year, a major severe weather event is followed by a period of calmer days. A ridge of high pressure rebuilds, the jet stream relaxes its grip, and the atmospheric ingredients separate, allowing the system to reload from a neutral state before the next round. This is the natural rhythm of spring in the central United States. Storm, then quiet, then storm again. It is like a heartbeat with a long, diastolic pause. But the year 2026 seems to be missing that pause. The diastole is absent. Instead of dissipating, the systems are overlapping, a behavior that fundamentally changes how we must interpret what is happening. And while flood warnings persist, another phenomenon is layering on top of them, one that might have been missed by anyone, only casually watching the forecast. A wall of cold air is sweeping down across the central and eastern United States, bringing temperature drops of 15 to 30 degrees Fahrenheit. This cold is slamming into regions that, only days before, were experiencing highs in the 70s and 80s. This is no normal transition. It is a stark thermal shock. The agricultural consequences are immediate and severe. Crops that had broken dormancy during the preceding warmth are now facing a significant freeze threat. Across the Midwest and the Mid-Atlantic, farmers are now forced to calculate how much of their early growth will be lost. And even this is not the end of the sequence. The possibility of late-season snow is now emerging for parts of the Northeast, including the Adirondacks and areas of New England that were, on paper, well beyond their last frost dates. We are talking about the kind of anomaly that has residents looking out their windows in late April to see snowflakes falling on grass that was green just the day before. While snow in late April is not entirely unheard of in these regions, its timing is what makes it so remarkable. When stacked on top of the tornado outbreak, the subsequent flooding, and the severe cold intrusion, it forms a pattern that cannot be dismissed as simple spring variability. What becomes clear is that we are not observing a series of separate weather events. This is one cohesive, multi-phase system that is behaving like a single organism with many limbs. The tornado outbreak was one limb, the flooding is another, the freeze is a third, and the reload we are about to witness on April 23rd is the next extension from the same body. You do not get this kind of synchronized sequence from random atmospheric noise. It is the product of a system with a dominant driver pushing it relentlessly forward. Consider this analogy. A normal atmospheric pattern might resemble a series of firecrackers, each one loud and brief, with periods of silence in between. What we are witnessing now is fundamentally different. It is a conveyor belt. The belt is in constant motion, and the next package continually arrives. The machinery does not pause between deliveries because it is not designed to. It is designed for continuous production, and it will keep operating as long as the force behind it remains in place. And here, the central thread of this entire pattern tightens. A conveyor belt implies a motor. A repeating pattern implies a forcing mechanism. A system that refuses to reset implies that something is locking this atmospheric configuration in place. That something is the very same element that made the April 17th event so predictable in the first place. It is the same force that made the April 23rd reload visible days in advance, and the same one that is quietly redrawing the map of where severe weather appears this year, and where it is strangely absent. Each new pulse builds upon the last. The ground is left more saturated than it should be, with soil soaked in places it normally would not be in mid-April. The rivers are running higher, and the air masses clashing overhead are more sharply defined. Every time the system cycles, it leaves the region slightly more primed for the next pulse. This continuity, in both hydrology and temperature, is a key to understanding why the 2026 pattern is so highly structured. The structure is being reinforced by the residue of each preceding event. So, when we arrive at April 23rd, we are not watching a new weather system appear on a clean slate. We are watching the next wave impact ground that is still wet, air that is still charged, and a jet stream that is still locked into a powerful position. The event this wave is about to generate is something that, in any other year, would be the biggest weather story of the month. This year, it is merely the next scheduled delivery on a conveyor belt that no one seems to know how to turn off. And the shape of what it produces will tell us everything we need to know about the driver behind it all. To grasp why forecasters are speaking with increasing caution about the 2026 season, we must turn our attention to the events forecast for April 23rd. This is not merely another day of severe weather. It is a convergence of atmospheric hazards so extraordinary that it strains belief. A tornado outbreak is anticipated across the plains and Midwest, mirroring the geography and ingredients of the April 17th event. Simultaneously, blizzard conditions are predicted for Montana and Wyoming, with heavy snow and powerful winds threatening to drop visibility to nothing and leave travelers stranded. In the same 2-4-hour period, a critical fire threat will emerge across Texas, Oklahoma, and Kansas, prompting red flag warnings for an environment so dry and windswept that any ignition could race for miles. And to complete this picture, intensifying floods are expected in the upper Midwest as already swollen rivers absorb yet another deluge of rain. Tornadoes, blizzards, wildfires, and floods all are projected to occur on the same day, spawned by a single, colossal weather system. It begs the question, what kind of atmospheric engine could orchestrate such a diverse and dangerous symphony? Let us pause to consider the magnitude of this forecast. In a typical year, any one of these four threats would command the national spotlight, dominating news cycles as a major weather story. It is exceptionally rare to see a tornado outbreak and a blizzard occur on the same day, as these phenomena are born from fundamentally opposite conditions. Tornadoes thrive in warm, humid, and unstable air, while blizzards require an atmosphere that is cold, dense, and dry. They are events that belong to different temperature profiles, humidity levels, and pressure systems. And yet, on this day, they are forecast to exist within the same overarching weather pattern, separated by just a few hundred miles. This is where we must introduce the concept of a compound event. We are not witnessing four distinct weather narratives, but rather a single, powerful atmospheric engine generating four different types of hazardous weather concurrently. The system's ability to produce such varied outcomes is rooted in its very structure. At its heart lies a deep upper-level trough moving out of the Rocky Mountains, which is coupled with a potent surface low-pressure system predicted to deepen to approximately 987 millibars. For late April, this is an exceptionally intense low. A pressure reading this low is more characteristic of a powerful winter nor'easter than a typical springtime system on the plains. This profound depth is the key. When a low becomes this strong, it can act as a vast atmospheric machine, simultaneously drawing warm, moist air from the Gulf of Mexico on one side and pulling down frigid Canadian air on its opposite flank. This dynamic creates the perfect conditions for multiple forms of severe weather to be manufactured at once. Let's explore the different components of this weather machine. In the warm sector, located to the east and southeast of the low, a river of moisture from the Gulf of Mexico is pulled northward. This air becomes highly unstable and interacts with strong wind shear from the overhead jet stream, creating a veritable factory for tornadoes. Meanwhile, in the cold sector, to the north and west, frigid, dry air wraps around the back of the storm. As this cold air encounters any lingering moisture, it generates heavy snow and potential blizzard conditions. Finally, we have the dry line, an invisible but critical boundary on the system's southern flank. Here, humid Gulf air collides with arid desert air from the southwest. As this line is drawn eastward across Texas and Oklahoma, the air to its west transforms into a tinderbox. Temperatures are expected to exceed 90 degrees Fahrenheit, with humidity plummeting to between 5 and 15%. Combined with fierce winds, these conditions mean any spark could ignite a wildfire that spreads uncontrollably. One system, 4 distinct hazards, all powered by the same atmospheric engine. It is at this point that the 2026 pattern begins to look less like a series of random weather events and more like a deliberate signature. These multi-hazard compound events, especially on this scale, are far from normal. They are so infrequent that when one does occur, it often becomes the subject of scientific research papers. The fact that such an event is appearing as the next reload in an already repeating sequence suggests that the underlying driver of this pattern is exerting immense pressure on the atmosphere. It seems to be a force powerful enough to make these extraordinary compound events a routine occurrence. The fire threat in particular warrants a closer look, as the projected numbers are truly startling. Across portions of the southern plains, conditions are forecast to reach the 90th percentile for dryness, with relative humidity dropping into the single digits in some areas. This is not merely dry. It is an extreme aridity, where static electricity crackles in the air, and vegetation, which should be green and moist, becomes exceptionally flammable for April. In most years, late April in the southern plains is a time of greening landscapes and sufficient humidity, making major fire weather a secondary concern. But this year is different. On the very same day that tornadoes are a threat in Kansas, red flag warnings for fire are being issued in Texas. This stark contrast perfectly illustrates the difference between simple complexity and something far more organized. A complex weather day involves numerous, often chaotic and disorganized atmospheric events. A coordinated weather day, however, is one where multiple events unfold in an organized fashion, all stemming from a single primary cause. The distribution of these events follows a logical pattern that reflects the structure of the driving force. April 23rd is a textbook example of a coordinated event. The dry line, the warm sector, and the cold air wraparound are all positioned exactly where atmospheric physics would predict them to be. Every component is in place, and every part is functioning as expected within the larger system. It is this very precision that is so concerning. Such large-scale coordination, emerging from a system that is just the latest in a repeating sequence, is precisely what one would expect to see if a dominant atmospheric driver were locking the jet stream into a fixed pattern, steering storm systems across the country on a predictable schedule. The atmospheric pattern responsible for this four-pronged hazard event is the very same one that generated the severe weather on April 17th. It is the same pattern behind the series of outbreaks seen earlier in the month. This suggests the pattern will continue to produce such events for as long as its underlying driver remains active. And as we will soon explore, that driver is not expected to dissipate in the coming weeks. On the contrary, there are signs it is intensifying. But before we delve into the nature of that driver, there is another piece of the puzzle to consider, a subtle clue hidden in the timing and rhythm of these events. This cadence, which has been largely overlooked, may be the most telling fingerprint of the entire phenomenon. This brings us to the cadence of the season. If we were to plot the major severe weather events of 2026 on a calendar, a timeline would emerge. And on that timeline, a pattern begins to resolve a rhythm that, according to our current understanding of meteorology, simply should not exist. A distinct and repeating rhythm has taken hold of the weather across the central United States. Between the 1st and 5th of April, a series of outbreaks swept through the region. This was followed by another sequence from April 9th to the 16th, and then the major outbreak on April 17th, which represented the peak of an atmospheric arrangement that had been developing for days. Now, a new system is approaching, set to arrive between April 22nd and April 26th, with the 23rd identified as the day of highest risk. If we examine the timing, a clear pattern emerges. A space of roughly 6 to 8 days separates each major event. This regularity is profoundly unusual. A truly random atmosphere does not produce such even spacing. It creates chaotic clusters and unpredictable gaps. You might see 3 outbreaks in 10 days, then an empty 3 weeks, followed by 2 more in a single week. That is the signature of a chaotic tornado season. The even spacing we are witnessing, in contrast, points toward a cycle, and a cycle always implies an underlying mechanism. This is the cadence that reveals something larger is at play, a clear indicator that the 2026 season is being guided by more than just local conditions. That consistent 6 to 8 day beat is not a coincidence. It is a fingerprint pointing directly to the cause. The jet stream, that powerful river of fast-moving air high in the atmosphere that guides weather systems, is currently locked into a specific configuration. This setup is repeatedly sending waves of energy eastward from the Pacific Ocean. Meteorologists refer to each of these waves as a trough, a southward dip in the jet stream that draws cold air down from the north, while allowing warm, moist air to surge northward ahead of it. When one of these troughs is ejected from the Pacific and travels over the Rocky Mountains, the downstream effect across the plains and Midwest is the perfect recipe for severe weather. Because this jet stream configuration is so persistent, the troughs arrive one after another on a predictable schedule. The 6 to 8 day interval is simply the time it takes for one trough to move through the system and for the next one to take its place. This timing is not arbitrary. It directly reflects the wavelength of the Rossby waves governing the jet stream's behavior in this particular state. Seeing that wavelength repeat itself across an entire month of weather events is a sign that we are observing a stable atmospheric regime, not just a series of unrelated storms. If the atmosphere were behaving in a truly chaotic manner, the periods between severe weather outbreaks would look very different. The timing would likely follow a mathematical pattern known as a Poisson distribution, where intervals could be 2 days, then 12, then an entire month of calm, followed by a sudden cluster of storms. But that is not what the 2026 season is demonstrating. Instead, the year 2026 is pulsing, and a pulse always implies a driver. When we see a beat this steady, we are compelled to look for the source of that rhythm. This brings us to the concept of teleconnections, a term essential for understanding why this season is unfolding as it is. A teleconnection is a large-scale climate pattern that can influence weather across vast distances by altering global atmospheric circulation. The most well-known of these is the El Niño Southern Oscillation, or ENSO, which will be a central character in this story. In essence, ENSO influences the jet stream. The jet stream, in turn, influences where troughs form and how frequently they are ejected. And that process ultimately determines where and when severe weather will occur. So, when we observe that the 2026 tornado season is pulsing on a 6 to 8 day cadence, what we are really seeing is a teleconnection setting the tempo. The jet stream is locked in a pattern. That pattern is producing troughs on a schedule, and those troughs are generating outbreaks downstream. It's a cycle of pulse, reload, and reload. Each event may appear to be a separate storm, but they are all expressions of the same underlying atmospheric configuration. To help visualize this process, imagine a factory assembly line, engineered to produce the same product over and over again. Each item emerges from the line at a regular interval every 6 minutes, for example. If you were standing at the end of that line, you would see a steady stream of products, each one seemingly identical to the last. While you might be tempted to view each product as a distinct object, they are all in fact manifestations of the same machinery, emerging at a pace dictated by that machinery. This is a powerful analogy for what we are witnessing in the atmosphere. One dominant pattern is expressing itself multiple times, on a schedule that reflects the fundamental speed of the system producing it. This realization reframes everything. If the 2026 season is simply one pattern repeating itself, then the most important question is no longer, when will the next outbreak happen? Instead, the question becomes, when will this entire pattern end? The answer to that question lies with the driver itself, how persistent it is, and whether its influence is set to weaken or strengthen in the coming weeks. These are not simple forecasting questions. They are questions about an entire atmospheric regime, and the atmosphere is telling us, quite clearly, that we are in a regime, not a series of random accidents. Yet, even this is not the complete story. The most telling piece of evidence for this overarching pattern is not found in what is happening, but rather in what is conspicuously not happening. To find this missing piece of the puzzle, we must turn our gaze several hundred miles southeast of where all the action has been. We have to look at a region that should be the very epicenter of severe weather at this time of year, but is instead eerily and unsettlingly quiet. Here, the story takes its most curious turn, a turn that makes it clear this narrative must be told. The single greatest clue to what is driving the 2026 tornado season is not found in the storms over Wisconsin, Kansas, or Oklahoma. It is found in the profound lack of storms somewhere else entirely. Until you are able to see this absence, the true shape of the entire pattern remains invisible. I want you to consider where tornadoes are supposed to be occurring right now. If you were to ask a meteorologist back in 2019 where they would expect to see peak severe weather activity in mid to late April, their answer would not have been the northern plains. The answer would have been Dixie Alley. This is the region that encompasses Mississippi, Alabama, Tennessee, and the surrounding states. Over the last 2 decades, it has tragically evolved into one of the most dangerous severe weather zones on the entire planet. And yet, this year, it is silent. A region of the United States known as Dixie Alley has a long and sobering history, responsible for some of the most destructive tornado outbreaks the nation has ever witnessed. Its severe weather season typically reaches a crescendo in the late winter and early spring, with March and April historically being the most active months. During an April in Dixie Alley, the atmosphere is expected to be turbulent. It is supposed to generate powerful, long-track tornadoes, often under the cover of darkness. These are the kinds of rain-wrapped, violent storms that can tear across multiple states, dominating the weather news and leaving forecasters sleepless. This is the established baseline, a pattern observed to varying degrees over the last 5 Aprils. But the spring of 2026 is different. It is silent. Dixie Alley is experiencing its most tranquil severe weather season in 5 years. This is not a subjective feeling, but a conclusion supported by a careful analysis of the data, confirmed by multiple severe weather experts. The number of days the Storm Prediction Center designated with an enhanced risk over the southeast has fallen dramatically compared to the recent average. Reports of tornadoes are down. Across the board, significant severe weather events have become scarce. The very region that should be the most volatile part of the country is now making barely a whisper. Before dismissing this as simple year-to-year randomness, it is worth pausing to consider the stark contrast unfolding elsewhere. At this very moment, the plains and Midwest are being overwhelmed, struck by outbreak after outbreak in a relentless 6 to 8 day cycle. Meanwhile, the Southeast is experiencing a spring so quiet it could almost be described as calm. These two opposing realities are occurring simultaneously within a single interconnected weather system. This is not the signature of normal variability. While some years are naturally quieter than others, it is highly unusual to see such a perfectly mirrored displacement, with one region overloaded while the other is so conspicuously spared. When you witness this kind of clear geographic redistribution, you are likely not looking at chance. Instead, you are seeing a climate signal at work, rearranging the very ingredients for severe weather. This is where the central mystery of the season begins to take shape. The atmospheric pattern of 2026 is defined not just by the weather it is creating, but also by the weather it is suppressing. The immense energy that would normally fuel late-night tornado outbreaks across Alabama and Mississippi has not vanished. It has simply been relocated. The crucial question where that energy went, and why, is the key that unlocks this entire story. As we move forward, it is essential to hold one idea in mind. On April 17th, the atmosphere was not just active in the Midwest, it was simultaneously inactive in the Southeast. These are two sides of the same coin, two halves of a single overarching phenomenon. One region is bearing the full brunt of the pattern, while the other watches from the sidelines. Once you understand the reason for this profound redistribution, you begin to see that 2026 is no random tornado season. It is a textbook demonstration of a specific atmospheric regime, playing out in real time almost exactly as predicted by a peer-reviewed study published back in 2015. Something is fundamentally reallocating the atmospheric ingredients this spring, directing moisture, shear, instability, and lift where to assemble and where not to. The mechanism behind this shift is about to become the main character in our narrative. Once you see it, the season stops looking like weather and starts looking like choreography. To grasp the significance of this quiet spring, we must first understand what a typical season in Dixie Alley looks like when it is behaving as expected. Without this baseline, the current silence does not carry its full weight. In many respects, the storms of Dixie Alley are the most dangerous in the entire country. They have a tendency to form at night when people are asleep and may not hear the sirens, if they sound at all. The tornadoes are often rain-wrapped, concealed within a dense curtain of precipitation that makes them nearly impossible to see until they are directly upon you. These storms also tend to move with incredible speed, as the low-level jet stream roars across the region at 40 to 60 knots during major events. Furthermore, they frequently occur in areas with higher population densities and more manufactured housing than the open plains. A tragic combination that helps explain why Dixie Alley tornadoes have historically resulted in higher fatality rates. The seasonal timing for this region is heavily concentrated from late February into early May, with March and April marking the peak. This is the window when the Gulf of Mexico is warm enough to pump a rich supply of moisture northward. At the same time, the jet stream is active enough to provide the necessary wind shear, and the clash between lingering cold northern air and warm southern air is strong enough to generate explosive instability. Under these normal conditions, one would expect the Storm Prediction Center to issue enhanced or moderate risk outlooks for this region on a regular basis. You would anticipate multi-state outbreaks, extensive news coverage, and the familiar rhythm of a volatile spring in the southeast running at full volume. If you examine the data from 2021 through 2025, that is precisely the pattern you find. Year after year, the Southeast consistently contributed a large portion of the nation's total tornado count during the early and middle parts of spring. Some years were more intense than others, but the signal was always there, always recognizable. The year 2026 deviates from this baseline in a way that is impossible to ignore. The number of enhanced risk days over the Southeast this spring is conspicuously lower. The forecast maps that should be painted with oranges and reds over Alabama and Mississippi have instead been shaded with yellows and greens, or the risk areas have shifted entirely to the northwest. The storm reports that should be flooding in from the region are now just a trickle compared to the historical average. Analysts who monitor this region closely have been remarking on this anomaly for weeks. This is not one person's interpretation of the data. It is an observational consensus that something highly unusual is taking place. And while this might seem like a secondary topic in the broader story, its importance to the main thread cannot be overstated, as it provides a crucial clue to a much larger atmospheric puzzle. The unusual calm across the southeastern United States is a profoundly important part of this season's story. This region is typically a major contributor to the nation's tornado count in early spring, so its current suppression is not a minor detail. It is the other half of the atmospheric pattern we have been tracing. The plains and Midwest are overloaded with severe weather, precisely because the Southeast is underloaded. All the energy that would normally ignite outbreaks across Dixie Alley is being systematically rerouted, steered north and west. This specific redirection is the exact signature that a particular climate driver would produce if it were in command of the jet stream this spring. This suggests the silence in Dixie Alley is not a random occurrence, but a predictable outcome of the same force producing the structured cadence of storms elsewhere. The absence in the south and the presence in the Midwest are two symptoms of a single underlying condition, one that peer-reviewed climate science indicates should happen when the Pacific Ocean shifts to a warm phase. So, when you feel the strangeness of a quiet April in Dixie Alley, it is not just an odd year. It is a form of confirmation. The atmosphere is following a predictable script, and the fact that it is doing so with such precision is exactly why the entire 2026 season feels so structured, so predictable, and so unsettling once the larger picture comes into view. Part 7. The energy went somewhere else. This raises a fundamental question. If Dixie Alley is quiet while the plains and Midwest are loud, where did that energy go? Within an atmospheric system, energy does not simply vanish. It gets redistributed. It finds a new home and expresses itself in a different location. Mapping this redistribution is one of the most revealing exercises one can undertake this spring, as it shows exactly how the 2026 pattern is reorganizing the nation's severe weather geography. A look at the map reveals a distinct shift in activity, both northward and westward. The classic late winter to early spring pattern features a belt of severe weather running from Texas through Louisiana, Mississippi, Alabama, and into Georgia and the Carolinas. Instead, we are now seeing a corridor that extends from Texas northward through Oklahoma, Kansas, Nebraska, Iowa, and up into Wisconsin and Minnesota. The heart of the action has moved away from the deep south and is now centered on the central and northern plains and the upper Midwest. The daily outlooks from the Storm Prediction Center visually confirm this, day after day, with enhanced and moderate risk areas being drawn much farther north than is typical for this time of year. The ingredients themselves, the moisture, the wind shear, the instability, and the forcing mechanisms have all been redistributed. While Gulf moisture is still being drawn northward, it is now traveling much farther north before it encounters the strongest shear and lift. The jet stream is positioned in a way that directs trough ejections over the northern plains instead of the southeast. Similarly, surface low-pressure systems are tracking through the upper Midwest rather than the Tennessee Valley. All the same components are present, but they are being assembled in a completely different place. This is what atmospheric redistribution looks like. The total amount of severe weather this spring may not end up being dramatically different from an average year. By the time we reach the end of May, the total tornado count might even fall within the normal range. The critical difference, however, is the geography of where that severe weather is occurring. And that is the piece that truly matters, because it is the geography that determines who is at risk, when they are at risk, and what kind of preparations they need to make. Here is the element that connects this back to the larger theme we have been building. This redistribution is exactly what a specific climate driver predicts. This is not a case of random variation or atmospheric noise, but a clear pattern of redistribution. When the Pacific Ocean is in a certain state, the jet stream adopts a particular configuration. In turn, that configuration funnels severe weather into specific regions while steering it away from others. This is not speculation. It is a well-documented mechanism in the climate science literature, which we are about to explore. From the viewer's perspective, especially for those living in the plains or the Midwest, this season might simply feel like there are more storms than usual. It might feel as though things are getting worse, that the atmosphere is more active, or that something is ramping up. On a local level, that perception is entirely accurate. Those regions are indeed receiving more severe weather than they would in a typical year. But from a national perspective, the story is more nuanced. The total amount of severe weather is not necessarily higher. It is just highly concentrated in fewer regions. This concentration makes those areas feel overloaded, while other places, like Dixie Alley, feel eerily quiet. The same regions are being hit repeatedly. The sequence from April 1st through 5th struck the Central Plains and Midwest. The sequence from April 9th through 16th impacted roughly the same area. The April 17th outbreak was centered over Wisconsin and the upper Midwest, and the April 23rd event is forecast to hit the Plains and Midwest once again. The same ingredients, the same geography, the same targeting. This is not how a typical season behaves. A typical season moves around. In 2026, the systems seem to be parked in the same zip code, over and over. That consistency is what tells you the jet stream is locked in place. At this point, some of you are likely thinking, how can we be certain this is truly being predicted by science? How do we know this is not just a coincidence that happens to align with a general theory? That is a fair and important question. In fact, it is the very question you should be asking, as it separates rigorous analysis from mere hand-waving. So, let us now delve into the statistical weirdness of what is happening. When you examine the specific anomalies that have accumulated this spring, the argument that this is all random becomes very difficult to sustain. Part 8. Statistical weirdness. We can begin with EF3 tornadoes, as they offer the clearest way to grasp what is taking place. An EF3 is the category that includes winds from 136 to 165 miles per hour, representing the threshold for what are considered strong or intense tornadoes. The essential thing to understand about EF3 tornadoes is that they are, by their nature, rare events. Of all the tornadoes that form across the United States each year, a mere 3% achieve an intensity of EF3 or higher. The overwhelming majority are rated EF0 or EF1, causing comparatively minor damage. An EF2 signifies a much more serious threat, but an EF3 can level entire structures. The rare EF4 and EF5 tornadoes are powerful enough to reshape the landscape of civilization itself. And so, it was a deeply unusual event when, on April 17th, two separate EF3 tornadoes touched down in Wisconsin. Two in a single state on a single day. This event becomes even more significant when viewed through the lens of climatology, which is where the geographic peculiarity of this season truly begins to surface. Historically, Wisconsin is not a primary hotbed for powerful tornado clusters. While the state certainly experiences severe weather, the traditional heartlands for strong and violent tornadoes lie elsewhere. The highest concentrations have long been found in the Great Plains across Oklahoma, Kansas, Texas, and Nebraska, with a secondary maximum in what is known as Dixie Alley, covering states like Alabama, Mississippi, and Tennessee. Wisconsin, though not immune, is simply not where one expects to find this level of tornadic strength. For the state to witness two EF3s in one outbreak would be a major weather story in any year. But in 2026, it serves as a single, stark data point in a much broader pattern of northward displacement. The very geography of tornado activity appears to be shifting. The zones where these powerful storms cluster are migrating, moving away from their historical centers and into regions that would not normally brace for such an onslaught. When we compare this activity to historical averages for mid-April, the anomaly becomes even sharper. In a typical year, Wisconsin would lie on the far northern fringe of the severe weather zone, seeing significant tornadoes only occasionally and violent ones almost never. In 2026, however, Wisconsin found itself at or near the very center of the action, with powerful tornadoes clustering there. The state's climatological role had been fundamentally altered. This is where the concept of outliers clustering together reveals its importance. A single, unusual tornado in an unexpected place can be dismissed as a fluke. Weather, after all, is inherently chaotic. But when a series of highly unusual events begin to stack up, each one an anomaly in its own right, the combined probability of them all occurring by chance plummets towards zero. Consider the strange symphony of events. In April of 2026, we have witnessed an unusually high number of outbreaks, occurring with an almost metronomic regularity. These outbreaks have maintained a remarkably consistent geographic footprint, one that is shifted far north and west of the historical norm. This pattern has featured unusually powerful tornadoes, clustering in statistically unlikely states, all while the traditionally active Dixie Alley has remained eerily quiet. This is not one anomaly. It is a cascade of 6 or 7, all pointing in the same direction, all consistent with a single underlying driver. When anomalies align in this way, they cease to be statistical noise. They become a clear and urgent signal. While each of these deviations, taken in isolation, might seem plausible as a random occurrence, 2EF3S in Wisconsin is unusual but possible. A quiet April in Dixie Alley happens. Their combined probability tells a different story. When you multiply the chances of all these events happening together in a randomly behaving atmosphere, the result is a number that is, for all practical purposes, 0. The only way for so many anomalies to align this cleanly is if a systemic force is producing them all at once. Therefore, to state that the events of 2026 are not random is not speculation. It is what the statistics themselves demand. The atmospheric behavior this spring has been so strange that the null hypothesis of random chance fails. Something is the common thread coordinating these events, and as we will explore, the explanation has been sitting in a peer-reviewed journal for more than a decade, waiting for a year just like this one to reveal its predictive power. But before we delve into that scientific explanation, there is one more layer of this pattern to consider, a layer that explains why so many are failing to see what is happening right in front of them. It is the cognitive layer which governs how we perceive weather, categorize seasons, and define what feels normal. The 2026 season, on its surface, can appear deceptively familiar. And this illusion of normalcy is what masks one of the most structured and significant severe weather patterns in recent memory. It raises a crucial question. How can something so profound remain so hidden in plain sight? There is a common, almost casual response to the patterns I have described. It sounds something like this. There are always tornadoes in April. This is just what spring looks like. Why is this a big deal? It is essential to address this sentiment directly, because the very instinct behind it is what allows this season's true nature to go largely unnoticed by the public, even as forecasters and climate scientists watch with a growing sense of unease. The human brain is wired to track individual events, not the intricate patterns that connect them. When you see a news report of a tornado, your mind files it away as a singular incident. A week later, another report is filed as another separate incident. Unless you make a conscious effort to overlay these events on a map and a calendar, the mind does not naturally perceive the geometry of the season as a whole. You see a sequence of similar events, which reinforces your mental model of a typical spring, leaving the underlying pattern invisible. This tendency is a known cognitive bias. It is not a flaw in our thinking, but rather a fundamental feature of how we process the world. We are, by nature, event trackers, not pattern recognizers, at least, not without deliberate effort. And so, a highly structured season, like that of 2026, can unfold in full view, yet remain concealed. The events themselves, a tornado in April, flooding in the Midwest, red flag warnings on the plains, are all familiar. Each one, on its own, fits our existing categories of what spring weather can be. The crucial piece of information that they are all appearing in a repeating cadence as part of a coordinated continent-wide pattern is the part that requires deliberate analysis to see. This is the source of the gap between expert and public perception. Meteorologists and climate scientists have been observing the 2026 pattern with mounting concern precisely because they are trained to look at the overlays, to see the connections that transform a series of isolated events into a coherent and unsettling story. When experts examine the outlook maps, compare the timing of events, and track the geographic footprint of storms, they see the pattern that has been described here. They compute the statistics, and through this analysis, they perceive a highly structured season. The public, meanwhile, sees tornadoes on the news and thinks it is simply April in the Midwest, business as usual. While both perceptions are understandable, only the data-driven one is truly accurate. The season only appears normal on the surface. Beneath this facade lies one of the most organized, coordinated, and theoretically predictable severe weather patterns observed in years. This gap between a casual glance and a deep analysis helps explain why the pattern's full implications are not being more widely discussed. It brings us back to the central idea. The 2026 season is not a product of random chance, but of structure. Its appearance of normality stems not from being normal, but from its underlying structure being concealed within events that fit our preconceived notions of spring weather. If we peel away that layer of familiarity, we find an atmosphere that seems to be following a script. That script, as we will see, was written in a 2015 research paper and is now playing out in real time over the American heartland. Before delving into that paper, there is one more essential piece of context to consider. It illuminates why the 2026 season is unfolding in a manner that seems to defy what long-term climate trends would lead us to expect. It is a compelling wrinkle in the story, revealing an atmosphere being pulled in two opposing directions at once. For now, one force is dominant, while the other patiently awaits its turn. For the last several decades, the prevailing long-term trend has been a discernible eastward shift in tornado activity across the United States. This eastward migration has been documented by research from NOAA's National Severe Storms Laboratory and numerous peer-reviewed studies. The classic tornado alley, centered over Oklahoma, Kansas, and Texas, has been experiencing a relative decrease in tornado frequency. At the same time, the Southeast, particularly the Mid-South and portions of the Ohio Valley, has seen an increase. The causes behind this shift are complex and remain a subject of active scientific debate. They are thought to involve long-term changes in moisture transport, variations in atmospheric instability, and perhaps even decadal scale shifts in the behavior of the jet stream. If this long-term trend points eastward, one would naturally anticipate that Dixie Alley would become progressively more active compared to the plains over time. This is the direction the overarching climate signal indicates. Over many decades, the Southeast is projected to become more of a tornado hotspot, not less. So what are we to make of 2026? where a quiet southeast and an overloaded plains present the exact opposite of what the long-term trend predicts. What we are witnessing is the interplay of competing climate signals that operate on entirely different timescales. The long-term, decadal climate signal points toward more activity in the southeast and less in the plains. In contrast, the short-term, seasonal climate signal is driving more activity into the plains and suppressing it in the southeast. And for this particular spring, the seasonal driver has taken control. It is powerful enough to temporarily override the multi-decade trend. This is a crucial distinction, as it demonstrates that various climate signals do not always align in direction or timing. It is entirely possible to have a long-term trend pointing one way, while a short-term driver pushes forcefully in the other, dominating the weather patterns for months or even a year. This is precisely the situation at hand. The specific short-term driver exerting its dominance in 2026 is the El Niño Southern Oscillation, or ENSO, which, as mentioned earlier, functions on a seasonal to multi-year timescale and wields a profound influence over the jet stream. And this is where our central thread re-emerges. The reason the plains are so active, while the southeast is so quiet this spring, is not a contradiction of the long-term trend, but rather a superposition with it. The long-term eastward push of tornado activity is still present, operating on its decadal timescale. It has simply been temporarily overwhelmed by an ENSO-driven atmospheric regime that is rerouting severe weather westward and northward for this specific season. Once the current ENSO signal inevitably weakens, the long-term trend will likely reassert its influence, and the southeast will probably resume its role as a major tornado zone. But for now, this spring, ENSO is in command. The resulting pattern bears a distinct signature. We see it in the structured cadence of outbreaks, the geographic redistribution of risk, the statistical weirdness, the emergence of quad-hazard compound events, and the unnervingly quiet conditions in the southeast. All of these are hallmarks of a specific ENSO configuration reaching into the atmosphere and dictating where severe weather will manifest this spring. That configuration, and the science explaining its mechanics, is where our exploration leads next. In 2015, a team of scientists at Columbia University's International Research Institute for Climate and Society published a study that, in light of this spring's events, feels remarkably prescient. It is a paper that now seems essential reading for any meteorologist or weather enthusiast. The authors, John Allen, Michael Tippett, and Adam Sobel, published their findings in a peer-reviewed journal. Their central discovery was both elegant in its simplicity and profound in its consequences. They demonstrated, with quantitative data, that the El Niño Southern Oscillation modulates the geography of severe weather in the United States in specific and predictable ways, not in a vague or approximate sense, but with clear, data-backed specificity. It is worth pausing to absorb the full weight of this finding. This was not a speculative essay or a thought piece for a popular magazine. It was a rigorous, quantitative, and peer-reviewed study. The researchers analyzed decades of historical data on severe weather and ENSO phases, establishing a statistical link between the two that was strong enough to possess genuine predictive skill. In essence, they constructed a rulebook. They effectively showed that when the Pacific Ocean exhibits a certain state, severe weather will tend to concentrate in one region of the US, and when the Pacific looks different, that activity will shift elsewhere. And they backed up this rulebook with mathematics. The mechanism they identified is not shrouded in mystery once it is laid out clearly. It operates as follows. The temperature of the sea's surface in the tropical Pacific Ocean holds a powerful influence over atmospheric convection patterns throughout the tropics. This, in turn, dictates the position and strength of the jet stream as it flows over the vast expanse of the Pacific. This atmospheric river of air then propagates downstream, affecting the jet stream's configuration over North America. And it is this continental jet stream that ultimately determines where troughs will form, where low-pressure systems will track, and where the volatile clash of air masses that fuels severe weather is most likely to occur. It is a direct causal chain, a sequence of events that connects Pacific temperatures to the geography of storms. This is the rulebook. Under an El Niño, the pattern typically favors severe weather across the plains and Midwest in the early to mid-spring, while suppressing it in the southeast. Under La Niña, the opposite tends to happen, with heightened activity in Dixie Alley and a reduction across the plains. While the specifics are more complex, depending on the strength of the ENSO phase and the time of year, this fundamental rulebook is well understood. Now, if we compare that rulebook to the events of 2026, the parallels are striking. The plains and Midwest are experiencing a barrage of outbreaks, while the Southeast remains unusually quiet. This distinct northward and westward shift, occurring with a coordinated rhythm, is consistent with a persistent jet stream pattern. This is not just a rough approximation, it is a textbook match. The very pattern described by the Columbia team in 2015 is unfolding with remarkable clarity in the spring of 2026. It is as if someone took their research paper, sketched the expected signals onto a map, and then watched as the atmosphere colored perfectly within the lines. The predictive power demonstrated here is what is truly astounding, because the paper was published years before this season, long before anyone could have known what the Pacific Ocean would be doing in April of 2026. And yet, the principles it established have described this spring with incredible accuracy. This is not mere coincidence, it is science functioning as it should. A model is built, tested against future data, and if it consistently makes correct predictions, our confidence grows that it reflects something real about the physical world. We saw this pattern on paper long before it appeared on radar, which is precisely why the 2026 season is not a surprise, it is a confirmation. The outbreak of April 17th served as a confirmation of this rulebook. The subsequent reload on April 23rd is poised to confirm it once more. Even the silence across Dixie Alley is a form of confirmation, happening in real time. Every single data point this spring is landing exactly where the rulebook suggested it would. The cumulative weight of this evidence is what makes the season so distinctive. But there is a twist in this story, one that elevates the significance of everything we have been observing. We are not yet in a full-blown El Niño. The Pacific is still merely drifting toward its warm phase. The atmospheric response we are witnessing is what happens when the ocean is only leaning in that direction, not when it has fully arrived. This raises a profound and unavoidable question. If this pre-El Niño signal is already producing a season so structured, so destructive, and so coordinated, what will the full El Niño signal look like when it finally arrives? Before we can contemplate that, we must first understand the rulebook in greater detail, because the specific structure of ENSO and the way it translates to severe weather geography is a story worth understanding in its own right. The El Niño Southern Oscillation, or ENSO, is not a single static state. It is an oscillation, a natural cycle that moves between three primary phases over time. First, there is El Niño, which is defined by sea surface temperatures in the central and eastern tropical Pacific that are warmer than average. Its counterpart is La Niña, characterized by cooler than average sea surface temperatures in that same region. And between these two extremes lies the neutral phase, where conditions are neither clearly warm nor clearly cool. The transitions between these states unfold over timescales of months to years, with each phase producing its own distinct weather patterns across large portions of the globe, including the United States. Under La Niña conditions, the weather pattern across the continental United States during late winter and early spring tends to encourage severe weather activity across the southeast. During a La Niña, the jet stream configuration often keeps the storm track farther south. This positioning more readily allows moisture from the Gulf and the clash of air masses to set up over the Mid-South and the Tennessee Valley. This is a significant part of the reason why recent springs, when La Niña has been a dominant influence, have seen major outbreaks in the region known as Dixie Alley. It is not the only factor, but it is an important one. During El Niño conditions, this entire pattern shifts. The jet stream tends to follow a more southerly path across the Pacific and into the southern tier of the United States. This rerouting of moisture and storm systems actually favors severe weather activity farther to the north, over the Central Plains and Midwest, during the transition from late winter into spring. In many El Niño configurations for this time of year, the southeast tends to experience reduced severe weather activity. This happens because the storm track is repositioned, and the necessary ingredients for storms do not come together there as frequently. This is, of course, a simplification of a highly complex picture. The exact effects are contingent on the strength of the El Niño, the time of year, and other overlapping climate factors. But the basic signal is there, and it is this very signal that the Columbia team quantified back in 2015. This rulebook is not the product of a single event or even a single season. Its foundation is built upon decades of historical data, which means it represents a statistical relationship observed time and again across many different ENSO cycles. When La Niña appears, the pattern tends to look a certain way. When El Niño arrives, the pattern tends to look different. This kind of repeatability across multiple decades is precisely what scientists look for when trying to establish a causal relationship rather than a random correlation. It marks the difference between a single anecdote and a whole population of observations that all share a common, identifiable signature. The physical mechanisms that drive this rulebook are also well established. It all begins with the sea surface temperatures in the tropical Pacific, which influence atmospheric convection through the simple heating of the air directly above the water. Changes in tropical convection create ripples that travel outward through the atmosphere, much like waves spreading across a pond. These atmospheric waves ultimately alter the path and intensity of the jet stream in higher latitudes. This shift in the jet stream is a critical link in the chain, as it dictates where surface low-pressure systems form and travel. In turn, this determines where moisture is drawn from and where the conditions for severe weather are most likely to converge. This is not some inscrutable process. It is a well-understood sequence of physical events. Each step in this causal chain can be measured, modeled, and observed, contributing to the overall pattern we see. This represents a direct cause and effect mechanism, one that has been rigorously studied, quantified, and confirmed by numerous independent lines of research. The 2015 Columbia paper stands as a particularly influential study within this body of work, specifically for its success in establishing a predictive link between the state of ENSO and the geography of severe weather. Yet, it is not an isolated finding. It is part of a broad scientific consensus that recognizes ENSO as one of the primary forces modulating year-to-year severe weather variability in the United States. What this atmospheric rulebook suggests, especially in the context of the year 2026, is that the atmosphere is adhering to predictable principles rather than behaving randomly. While the immense complexity of the real atmosphere always introduces a layer of statistical noise around these patterns, the underlying signal is undeniably present. And this spring, that signal is emerging with a startling lack of interference, which is precisely why the resulting pattern is so recognizable. The 2026 season aligns with the established rules with a degree of precision that is, frankly, quite rare. In most seasons, one might observe faint echoes of the expected pattern, but they are often obscured by a great deal of noise. This year, the pattern is materializing with exceptional clarity. The signal-to-noise ratio is unusually high, and this fact alone is a significant piece of data. It tells us that whatever force is driving the weather this spring is doing so with immense strength and focus. To understand this driver, we must first ask, where are we in the ENSO cycle at this very moment? The answer to this question is essential, as it shapes how we interpret the events we have been witnessing and what we should anticipate in the weeks and months to come. The technical answer is that we are in an ENSO-neutral state that is rapidly trending toward warmth. The oceanic Nino index, the standard metric for the ENSO state, has been steadily climbing, moving from a reading of approximately negative 0.55 to about plus 0.16 inches recent months. For context, index values above plus 0.5 are classified as El Niño conditions, while values below negative 0.5 are considered La Niña. Anything in between is deemed neutral. A value of plus 0.16 is therefore on the warm side of neutral, and it is moving in that direction quickly. But this is only the story at the surface. Beneath the waves, a more dramatic narrative is unfolding. There is significant subsurface warming across the equatorial Pacific, highlighted by an eastward propagating Kelvin wave with temperature anomalies around plus 4 degrees C. In this context, a Kelvin wave is a vast, slow-moving pulse of warm water that travels along the equator. It eventually surfaces, playing a key role in the transition from neutral or La Niña conditions into a full-fledged El Niño. Seeing such a strong Kelvin wave is a clear harbinger, signaling that the ocean is priming itself to push surface temperatures even higher in the near future. Here we arrive at a subtle but crucial point about the atmosphere's relationship with ENSO. The atmosphere does not politely wait for an index to cross an official threshold before it begins to react. It reads the state of the ocean in real time, adjusting its circulation patterns based on what the ocean is actually doing, not what a classification system says. Therefore, even though we are technically still in ENSO-neutral territory, the atmosphere is already beginning to behave as if an El Niño is developing. It is responding to the oceanic signal that is actively building, not to a static index value. This insight is fundamental to understanding the 2026 season. What we are observing right now is not the atmosphere's response to a fully formed El Niño. Instead, it is the response to a pre-El Niño configuration, one where the Pacific is leaning warm and the atmosphere is beginning to adopt the corresponding circulation patterns. This is the key to deciphering the current events. We are witnessing pre-El Niño behavior. The atmospheric forcing is not yet at its peak strength, and yet the pattern is already producing the structured, coordinated, and rhythmic severe weather season we have been documenting. The resulting phenomena heightened activity in the plains and Midwest, a suppression of storms in the southeast, and a persistent jet stream configuration that produces a regular cadence of trough ejections are all precisely what the rulebook predicts for this early phase of the transition. We are seeing coordinated, compound events on the reload days, just as expected given the current state of the Pacific and the atmospheric response it generates. This leads to an unsettling conclusion, one that is difficult to articulate without sounding alarmist. What we have witnessed so far, as intense as it has been, is merely the prelude. The main event is what occurs when the El Niño signal fully matures and the atmospheric forcing intensifies. This is a prospect that every forecaster and climate scientist observing this setup is acutely aware of, even if they remain measured in their public statements. So, if this early phase manifests as 54 tornado reports on April 17th, compound quad hazard events on April 23rd, a steady 6 to 8 day rhythm of severe weather outbreaks, and a silent Dixie Alley, what might the full phase look like? What happens when the ocean fully commits to this new state and the atmosphere responds in kind? These are the questions we will explore in the final part of this analysis. But first, it is worth taking a brief detour to examine something that has been a persistent puzzle throughout this season. We must look at one of its most unusual features, a characteristic that demands its own focus. We need to ask, why does the pattern feel almost too clean? Weather systems are, by their very nature, noisy. This is a foundational concept in meteorology. The atmosphere is a high-dimensional, chaotic fluid, filled with small-scale variations that often seem to defy any large-scale signal. Most of the time, when a climate driver like ENSO influences weather, its effect is seen as a statistical tendency, not an unbreakable rule. The signal is there, but it's often buried in chaos. In the study of weather, statistical analysis often reveals a bias, a subtle signal that confirms a theory, but is rarely a perfect match to observation. This signal is typically buried within a great deal of atmospheric noise, requiring scientists to average data over many events to see the underlying pattern emerge with any clarity. Even during severe weather, seasons heavily influenced by phenomena like ENSO, this inherent messiness is the norm. The result is a general tendency toward a predicted pattern, but one that is littered with individual events that defy the forecast unexpected outbreaks, quiet periods in normally active zones, and complex weather events that don't align neatly with their expected synoptic setups. This is the natural state of atmospheric science, a field where meteorologists work to extract that faint signal from the noise, all while accepting the atmosphere's fundamental unpredictability at finer scales. The 2026 season, however, presents a starkly different picture. In fact, it seems almost too clean, too orderly. The very pattern described by the Columbia team back in 2015 is materializing with an unusual and startling clarity. The geographic redistribution of weather events is textbook, the cadence of their arrival is regular, and the suppression of activity in Dixie Alley is dramatic. The overloading of the plains is pronounced. The necessary ingredients for storms are arriving on schedule, and compound events are assembling precisely as the synoptic structure would predict. It is as if the background noise of the atmosphere has been quieted, allowing the core signal to broadcast with exceptional strength. The best way to describe this phenomenon is to say that the signal-to-noise ratio this spring is unusually high. The underlying pattern is being revealed with more precision than is typical, because some force is pushing on the atmosphere hard enough to overcome its usual chaos. That force is almost certainly the immense strength of the Pacific forcing, which is building even before El Nino has been officially declared. The Kelvin wave, the subsurface warming, and the trending oceanic Nino index are all combining to produce an atmospheric influence of extraordinary coherence, a coherence now reflected in the severe weather pattern. A high signal-to-noise ratio in a climate-driven weather pattern is a rare occurrence, the kind of anomaly that captures the attention of researchers. It suggests that the forcing from the Pacific is exceptionally strong when compared to the atmosphere's own internal noise. In simpler terms, the Pacific is shouting its influence, and the atmosphere is hearing it so clearly that the resulting weather pattern is almost a perfect illustration of theory. This is where the scientific observation carries a different kind of weight, because the very clarity of the pattern is evidence that it is structured and not random. A truly chaotic atmosphere would not generate this degree of coherence. A randomly varying year-to-year signal would not align so cleanly with a published theory. The fact that the 2026 season looks like a flawless example from the 2015 Columbia paper is a data point in itself. And this data point tells us that the driver behind this season is both powerful and persistent. This clarity should inform how we consider what comes next. If the pre-El Nino signal is already producing a pattern this defined, it raises an urgent question. What might a stronger, fully developed ENSO signal produce? We shouldn't necessarily expect the pattern to become even cleaner. but the intensity of the forcing is likely to scale with the ENSO state. A stronger forcing implies a more pronounced pattern, with more outbreaks, more coordinated events, and a more dramatic geographic redistribution of weather. It suggests an amplification of everything we are already witnessing. This potential amplification would not be a surprise, as the mechanism producing the pattern is well understood. It is the same machinery we have been tracing, and the same one that is about to demonstrate its power once again in the next cycle. To understand this season's persistence, we must examine the physical components of what can be called the weekly reload mechanism. The key to the 2026 pattern is its distinct pulse, a cadence of roughly 6 to 8 days, and grasping why this is happening is crucial to understanding why it is likely to continue as long as the underlying driver remains in place. The mechanism itself is a beautiful example of how large-scale atmospheric processes fit together with elegant precision. The engine of this entire season is a series of troughs ejecting from the Pacific Ocean. To understand this, we must visualize the jet stream, the high-altitude river of fast-moving air that encircles the mid-latitudes. This river does not flow in a straight line. Instead, it meanders in a series of ridges and troughs. Ridges are northward bulges, where the jet stream arcs toward the pole, while troughs are southward dips where it plunges toward the equator. This ridge-trough structure, known as Rossby waves, is not static. It propagates eastward over time. In the specific configuration of 2026, the jet stream is arranged in such a way that troughs are repeatedly cast out from the Pacific, crossing the Rocky Mountains and emerging into the central United States. Each of these troughs brings with it a low-pressure system, which pulls a surge of warm, moist air from the Gulf of Mexico ahead of it, setting up a clash with the cold, dry air trailing behind. This collision of air masses provides the essential cocktail of ingredients for severe weather. And because the jet stream is locked into this persistent configuration, the troughs continue to arrive, one after another, almost on a schedule. The sequence within each cycle unfolds predictably. First, a trough approaches from the west, visible on forecast models several days in advance. As it nears, moisture from the Gulf of Mexico begins to surge northward, drawn in by the strengthening southerly flow ahead of the trough. As the system moves over the Rockies, the surface low-pressure system deepens, a process aided by upper-level divergence that allows the surface pressure to fall. The warm sector to the southeast of the low becomes unstable and sheared, while the cold front on the western and northern edge provides the trigger. Storms ignite along the dry line and the cold front, and if all the parameters align, tornadoes can develop. The system then tracks eastward over the next day or two, leaving a path of severe weather before it dissipates or transitions into a more mature cyclone farther east. And then, the next trough arrives from the Pacific, and the entire cycle repeats. The reason for this relentless repetition is the persistent configuration of the jet stream, which is being held firmly in place by the dominant climate driver of the moment, the powerful Pacific forcing associated with the trending El Nino. When a powerful atmospheric forcing remains in place, the jet stream responds with a predictable rhythm. It will continue generating troughs at a consistent cadence, which in turn triggers severe weather in the same regions and at the same intervals. That 6 to 8 day spacing is not an arbitrary figure. It is a direct reflection of the Rossby wave's wavelength within this specific jet stream configuration. A different arrangement would yield a different wavelength and, consequently, a different tempo. For now, this is the rhythm the atmosphere has found. The remarkable consistency of this timing across multiple storm outbreaks this spring is the signature of a highly stable atmospheric regime. This creates a feedback loop in the truest sense. The Pacific Ocean acts as the primary force on the jet stream. In response, the jet stream produces troughs, which then generate severe weather. That weather alters the local environment through hydrological and thermodynamic changes, effectively setting the stage for the impact of the next trough. The cycle repeats, with each new iteration building upon the conditions left by the last, continuing until the underlying oceanic forcing shifts. It is the same engine, simply running through different iterations. This perspective is essential for understanding the 2026 tornado season. Each outbreak is not a distinct event, but a new expression of the same fundamental machinery. The period from April 1st to 5th was one iteration, followed by another from April 9th to 16th, another on April 17th, and yet another on April 23rd. These iterations will persist as long as the engine is running. And that engine is being powered by the Pacific Ocean. This reframes the entire season. We are not witnessing a series of separate events, but rather one continuous system manifesting in multiple phases. This explains why the pattern has been so stable and persistent. Stable systems do not easily break down. They continue producing their output until the force sustaining them changes. And in this case, the forcing from the Pacific Ocean is not just holding steady, it is strengthening. This suggests the pattern is not only set to continue, but it is likely to intensify. So, what happens when that forcing increases? What is the consequence when the Pacific fully transitions into El Nino and the atmosphere's response scales up? This is the question that looms over the remainder of spring and into summer, and it is a question we must confront, because the answer science is pointing toward is not a comforting one. If this destructive, structured, and predictable tornado season is what occurs while the Pacific is only drifting toward El Nino, it raises a question that every forecaster and climate scientist is quietly asking. What happens to this pattern when El Nino fully arrives? This is the central question of escalation for the entire season. While we may not know the answer in precise detail, we can still reason about its likely direction. The most straightforward expectation is that a stronger forcing from the El Nino Southern Oscillation, or ENSO, would generate a proportionally stronger atmospheric response following the same general patterns we are already observing. This stronger response could manifest in several ways. It might lead to more powerful outbreaks, with a higher number of tornadoes per event, and, specifically, more violent tornadoes. It could also mean the pattern persists for longer, extending the severe weather season later into the year than is typical. Another possibility is an expansion of the geographic impact, with the currently overloaded zones spreading into more of the northern plains and the upper Midwest. It could even shift farther north as the jet stream makes its seasonal retreat into summer. Of course, none of these are guaranteed outcomes. The atmosphere is an incredibly complex system, and its exact reaction to a strengthening El Nino will depend on numerous factors. These include how strong the El Nino ultimately becomes, the speed at which it develops, and its interaction with other global climate signals. However, the general trajectory of the likely response points toward an intensification of what we have already seen, not a moderation. It is improbable that this pattern will simply fade away. It is far more likely to amplify. This general expectation is supported by forecasts from the Climate Prediction Center. Current probabilistic outlooks place the likelihood of full El Nino conditions developing later this year between 61% and 70%, with the exact figure depending on the specific time frame and analytical method used. This represents a clear majority expectation among forecasters. The Pacific is anticipated to continue its warming trend. The atmosphere is expected to continue responding, and the severe weather pattern, already in motion, is forecast to persist and likely strengthen. There is another, lower probability scenario that warrants consideration. Some analyses estimate the chance of a super El Nino, an event of unusually high intensity, at around 25%. A super El Nino would be the kind of event that could force the atmosphere into an extreme version of the patterns we have been discussing. While it is not the most probable outcome, it remains a plausible one, with profound consequences for severe weather in the United States and for climate patterns around the globe. Let me be clear, this is not a guarantee. The Climate Prediction Center is not stating that a super El Nino is definitely coming. They are identifying it as a plausible scenario with a meaningful probability. And probability is not the same as prediction. The most likely development is a moderate to strong El Nino over the coming months, with the severe weather patterns scaling up in response. But the tail risk of a super El Nino is real, and it is a significant reason why the 2026 season is being monitored with such intense focus. The bottom line is that the current pattern could intensify. If it does, the rest of this spring and the following summer could become a very different experience for the parts of the country already being impacted. This could mean more outbreaks, more compound events, more reload cycles, and a potentially wider geographic reach as the pattern shifts with the seasonal retreat of the jet stream. In that sense, what we have witnessed this April, as intense as it has been, may only be a preview rather than the peak. The true peak, should El Nino develop as expected, might be something this season has not yet shown us. That is a sobering thought, but it is what the science currently indicates. To pretend otherwise would be a disservice to the people who must prepare for what may be on the horizon. This is not about causing alarm. It is about conveying the serious implications of the scientific data. This analysis is rooted in the best available climate science and the most current oceanic and atmospheric data. For the 2026 season, a predicted pattern is tracking with unusual clarity, and the force driving it is growing stronger. This suggests the pattern itself will likely intensify a prospect that carries serious implications for all those in its path. To understand this, we must first explore a broader context from climate research, the concept of compound events. For several years, assessments from bodies like the Intergovernmental Panel on Climate Change have highlighted these phenomena where multiple hazards co-occur. They happen in the same place and time, or in connected regions, producing impacts far greater than the sum of their individual parts. The quad hazard event of April 23rd serves as a textbook example of just such a compound event. Climate science literature has documented a clear increase in the frequency and intensity of these compound events over recent decades. This trend appears to be driven by a variety of factors, from changes in atmospheric circulation to increases in available moisture and energy. It also includes shifts in the distribution of the ingredients needed for extreme weather. Specifically, researchers have recorded a growth in environments that support high convective available potential energy, combined with strong wind shear, the precise conditions that generate severe thunderstorms and tornadoes. This trend is a key signal that climate scientists reference when discussing how our changing climate affects severe weather, though the specific link between climate change and tornado counts remains a subject of active research without definitive conclusions. In the context of the 2026 season, this means the ENSO pattern we are analyzing is not operating in a vacuum. It is unfolding on top of a baseline atmospheric state that has been fundamentally shifting over time. This new baseline is one in which the ingredients for severe weather are, on average, more plentiful than they were in the past. It is a crucial piece of the puzzle for understanding what may lie ahead. Therefore, when an ENSO pattern works to assemble those ingredients into a particular geographic configuration, the severity of the weather that results can be amplified by these underlying changes in the environment. This is why it is so important to connect this idea back to the central story of this season. The 2026 pattern is not merely ENSO at work. It is ENSO operating on a foundation that has evolved. The same signal that would have produced one outcome 30 years ago is now acting on an environment with more available energy, more moisture, and, in many areas, more shear. This means when the pattern comes together, it can produce events that are more intense or impactful than the same pattern would have in decades past. Compound events, as the research suggests, are becoming more common, and the April 23rd quad hazard event aligns with that trend. The implication is not that these events are unprecedented in an absolute sense. Rather, it is that they are trending in a direction where we should anticipate seeing them more often. The 2026 season, with its repeated reloads of compound event potential, provides a valuable window into what that future might hold. It is a case study in what happens when a specific climate driver, in this case, ENSO, operates on a baseline that has been evolving for decades. It shows how such events emerge from the interaction of multiple climate signals and how predictive science is racing to comprehend the atmosphere's growing complexity. Now, it is important to address a subtle but significant limitation within the world of forecasting that is relevant to our discussion. Understanding this is essential for how we should think about seasons like 2026, as it highlights both the power and the boundaries of our predictive tools. Short-term storm prediction is, without a doubt, one of the great success stories of modern meteorology. In the last couple of decades, models like the high-resolution rapid refresh and the North American mesoscale model have achieved a level of skill that would have seemed nearly impossible to forecasters of a previous generation. A severe weather outbreak can now be anticipated days in advance with stunning specificity, its evolution tracked in near real time with radar and mesoscale models. The warning systems that helped ensure the low casualty count on April 17th are a direct product of this incredible progress, representing an enormous investment of scientific and technological effort over many decades. However, in the realm of regime shifts and large-scale pattern recognition, our models are still developing. The very same models that can masterfully predict a tornado outbreak 4 days out may not be as skilled at anticipating multi-month regime shifts, nor can they always capture the full implications of a strengthening ENSO signal for the geography of severe weather. This is not a criticism of the models, but rather a frank acknowledgement of where the science currently stands. This capability gap creates what you might call a blind spot. A forecaster can, with high confidence and specificity, predict what is going to happen on Thursday, but getting a clear read on what the entire spring will look like, based on the atmospheric regime it has entered, requires a very different type of analysis. That analysis is harder to perform with the same level of confidence. While it is possible, and the work by the Columbia team is one example of how it can be done, it is not where the bulk of operational forecasting effort is concentrated. This means the structural pattern we have been identifying in 2026, the way it is tracking a specific, climate-driven regime, may be something that does not register cleanly within the traditional forecasting framework. The individual events are being forecast exceptionally well, but the larger architecture that connects them, the overarching pattern, can be missed. This raises the question of what we fail to see when we focus only on the immediate storm, rather than the climate shaping the season. The larger climate regime that shapes these events is often more apparent to researchers studying phenomena like ENSO and severe weather teleconnections than it is to operational forecasters, whose work is rightly centered on immediate, near-term specifics. This is not an oversight by the operational community, but rather a reflection of different professional priorities. While many forecasters are deeply knowledgeable about the ENSO context, their primary role is to focus on the immediate future. This leaves the broader questions about overarching climate regimes to be explored more within research and climate prediction circles. In a sense, the science itself may be lagging behind the system-level changes we are witnessing, as our tools for recognizing and responding to such regime shifts in real time are still under development. We have the theoretical frameworks and foundational studies, like the notable paper from Columbia. But the process of integrating that knowledge into operational forecasting and public-facing communication is still very much in progress. A season like 2026, where the weather pattern so cleanly follows a predicted regime, offers a rare opportunity to test and refine that very integration. This brings a critical question to the forefront. Are we underestimating the potential persistence of these patterns? The answer matters deeply. If the 2026 pattern endures as long as the theoretical framework suggests it should, while our operational sense of its decay is calibrated to more chaotic atmospheric norms, we could be caught off guard by its longevity. The pattern's unusual clarity, driven by a distinct climate signal, is what makes it so compelling. As the forecasting community watches the daily events unfold and the research community analyzes the overarching structure, the interaction between these two perspectives has become one of the most important conversations in atmospheric science today, one that will undoubtedly shape how we prepare for similar seasons in the future. Whenever a weather pattern manifests with this degree of cleanliness, predictability, and coordinated appearance, a certain collection of alternative theories inevitably begins to circulate. It is worth taking a moment to address them, not to lend them credence, but because they represent a significant cultural response to such phenomena, and direct engagement is more useful than pretending they do not exist. You have likely already seen some of these ideas circulating on social media, especially in the days that followed the April 17th outbreak. They appear in the comments of weather analyses and are posted alongside radar imagery with captions implying that someone is steering the storms. This reaction is, in its own way, understandable. When a natural event appears too coordinated, the mind instinctively searches for an explanation that matches that feeling of intention, and a scientific explanation often fails to satisfy this, even when it is correct. These theories tend to reference specific programs and technologies. One is the High-Frequency Active Auroral Research Program, better known as HAARP, which is a research facility in Alaska dedicated to studying the ionosphere. Another common reference is to cloud seeding, a real but limited weather modification technique sometimes used to enhance snowfall over mountain watersheds. Occasionally, the theories venture into more exotic territory, citing directed energy weapons or other technologies supposedly capable of producing or guiding severe weather. The 2026 season, with its pristine structure, is precisely the kind of event that attracts such speculation. The clean cadence of the storms, their specific geographic targeting, and the compound events that seem almost staged in their presentation, all invite a form of pattern matching that observes a coordinated system and assumes a coordinator. These explanations, however, fail when scrutinized against fundamental physics for reasons that are worth stating plainly. The first and most definitive reason is the sheer scale of energy involved. The energy within severe weather systems is astronomically larger than anything any known technology can meaningfully influence. A single thunderstorm, not an entire outbreak, but one storm releases energy on the order of tens of thousands of hydrogen bombs. Let that number settle for a moment. A multi-state severe weather outbreak then releases energy many orders of magnitude larger than that. We are talking about figures that have no useful analogy in our everyday experience because nothing we encounter operates at that scale. No technology on Earth can input enough energy to steer or generate these systems at the scale we are observing. Even the output of the world's largest power plants is trivially small compared to the energy moving through a single supercell thunderstorm in a single hour. Furthermore, a fundamental separation exists between the atmospheric layers, where these technologies are said to operate, and where weather actually happens. Facilities like HAARP function in the ionosphere, a region that sits roughly between 50 and 600 miles above the Earth's surface. In stark contrast, all weather, every tornado, thunderstorm, and hurricane you have ever experienced takes place in the troposphere, the dense bottom layer of the atmosphere, extending only 10 to 15 miles upward. These are not adjacent zones that casually interact. They are distinct realms separated by other atmospheric layers, behaving according to different physical rules with different densities, temperatures, and energy flows. The idea that manipulating one could meaningfully reorganize the other on a continental scale is not supported by any physics we understand. Cloud seeding, meanwhile, is often cited as if it were a proof of concept for weather control, but it is not. It is a real technology, but its capabilities are extremely limited. Cloud seeding can produce small, localized modifications to precipitation under very specific conditions, such as slightly enhancing snowfall over a targeted mountain range when the right kind of clouds are already present. It cannot produce tornadoes. It cannot generate severe weather outbreaks. It cannot reorganize the geography of severe weather across a continent. It cannot route a jet stream, suppress activity in Dixie Alley while simultaneously overloading the plains, or schedule troughs to eject from the Pacific on a precise 6 to 8 day cadence. The forces at play are simply on another scale entirely. The chasm between the actual capabilities of cloud seeding and what would be necessary to generate the 2026 weather pattern is so immense that the comparison simply dissolves under scrutiny. I can appreciate the frustration that often gives rise to such theories. After all, I sometimes explore fringe topics on calm space, and I am not one to instinctively reject unconventional ideas. Instead, I believe in taking them seriously enough to examine the underlying physics. When the science does not align, I am compelled to say so. In this instance, the physics offers no support whatsoever. These exotic explanations collapse when tested against energy budgets, the separation of atmospheric layers, geographic scale, and the specific mechanisms required. They are not merely incorrect, they are off by orders of magnitude. These ideas persist because the pattern itself feels so unnatural, and the human mind has a tendency to grasp for extraordinary causes when ordinary ones seem insufficient. There is a well-documented cognitive bias to favor intentional explanations over coincidental ones, particularly when a phenomenon is vast, frightening, or has personal consequences. A coordinated series of destructive weather events certainly meets all three criteria. It can feel as though someone must be responsible, because the alternative that the Earth's climate system can orchestrate this level of complexity on its own is, in some ways, even more disquieting. At least a villain with a weather machine is a concept we can comprehend. An entire ocean basin silently reorganizing a continent's weather is a far more abstract and humbling reality to accept. Yet, the natural explanation is vastly more robust than any of the exotic alternatives. The ENSO-driven atmospheric regime, which we have been tracing, successfully accounts for the pattern's structure, its distinct cadence, its geographic redistribution, and its compound events. It also explains the statistical anomalies and aligns perfectly with decades of peer-reviewed science. This framework doesn't just explain a few pieces of the puzzle. It provides a coherent and testable model for all of it. The power of such a model is that it leaves no significant observation unaccounted for. Every single observation we have examined, from the outbreak on April 17th to the unusual silence in Dixie Alley and the quad hazard reload on April 23rd, fits neatly within the ENSO framework without any need for contortion. This framework was not created after the fact. It existed long before this season began. The events of this season are now serving to confirm the model's predictive power. This is the very essence of scientific validation, and it represents a standard of proof that none of the exotic alternatives can approach. The true cause is the ENSO-driven structure we have been meticulously following. This is not speculation. It is the established consensus of the climate science community, which the 2026 season is now confirming in real time. It is worth noting how fundamentally different this explanation feels from the others. The ENSO explanation requires no secret facilities, no classified technology, and no vast human conspiracy. It only requires the Pacific Ocean, an entity that is right there, openly monitored by satellites, buoys, and research vessels from numerous countries, to behave in a way that has been documented for decades and predicted in published literature. Everything is in the open, the data is public, the mechanism is published, and the observations are verifiable. The pattern feels unusual because, in a sense, it is. A season that so cleanly tracks a specific climate regime is indeed rare. But it is crucial to understand that rare is not the same as unnatural. The atmosphere is fully capable of producing patterns of extraordinary clarity when the forcing is strong enough to overwhelm the system's usual background noise. That is precisely what is happening now. The Pacific is, metaphorically, shouting its instructions, and the atmosphere is listening. The result is a season that, for once, matches the theory with minimal static. This very clarity is what can make the season feel staged or artificial. But it is not staged. It is simply a rare window into the climate system when one of its primary drivers is operating at full volume. So, when you encounter these other theories circulating online, and you will, because the 2026 season is exactly the kind of event that attracts them, I hope you will remember what we've discussed here. The physics does not support them. The proposed mechanisms do not hold up to scrutiny. The exotic explanations fail at every scale of examination. Meanwhile, the natural explanation, the ENSO regime, holds true at every scale and accounts for every observation. This is not a coincidence. This is what a correct scientific explanation looks like. Recognizing that difference is what separates a viewer who sees the pattern clearly from one who gets lost in the surrounding noise. Let us return to where we began, because the purpose of this analysis is not to fixate on what is wrong, but to illuminate what is actually happening and what it means for the future. The events of April 17th were not a random anomaly. The 54 tornado reports, the 2 EF3S in Wisconsin, and the 750 severe weather reports in a single day were not the atmosphere rolling dice. They were the atmosphere reading from a script handed to it by the state of the Pacific Ocean. This script follows rules that have been documented and published for over a decade, and it is still being read in real time, chapter by chapter, across the American sky. I invite you to sit with this framing for a moment, because it has the power to change how you experience the rest of this spring. Once you see the script, you cannot unsee it. Every severe weather day, from this point forward, will look different. You will begin to notice the cadence. You will recognize the geography. You will observe the silence, where silence is not supposed to be. And you will realize that what appears to be chaos on the surface is, in fact, one of the most structured severe weather seasons the central United States has witnessed in recent memory. The shock of the events themselves may not diminish, but the element of surprise will. And replacing surprise with pattern recognition is one of the most valuable shifts in perspective a person can make. With this new understanding, April 23rd is no longer a surprise. It is a confirmation. The very same configuration that produced the events of April 17th is now producing the events of April 23rd. It is the same engine, the same ingredients, and the same geographic targeting. The quad hazard event that is currently assembling is not some exotic coincidence. It is the next logical and predictable passage in a story written by the ocean itself. This event is born from a precise atmospheric recipe, the result of a deep trough and a strong surface, low interacting with Gulf moisture and cold continental air. It is a choreography dictated by the current configuration of the jet stream. What we are witnessing is one more iteration of a pattern we have been observing, and it is far from the last. It will persist not just this week or this month, but for as long as the underlying atmospheric forcing remains in place. This great engine is still running, and it is scheduled to produce much more before it finds a moment of rest. The quiet in the traditional Dixie Alley might seem like a reprieve, but this is a meteorological illusion. The silence does not signify an absence of energy, but rather a large-scale redistribution. The power that would normally fuel late-night tornado outbreaks across Mississippi and Alabama has not vanished from the system. It is simply being rerouted because the ENSO-driven jet stream is anchoring it farther to the north and west. This redistribution is the other side of the overload being experienced in the plains. These are not separate phenomena. They are two symptoms of a single, unified condition. That underlying condition is the ENSO regime taking shape in the Pacific Ocean. The active region and the quiet one are telling the same story from opposite ends of the map, like two dialects of a single language. And this entire configuration was, in fact, predicted by science. In 2015, a team from Columbia University published a peer-reviewed study that quantitatively described how ENSO would alter the geography of severe weather in the United States. The pattern they detailed is the very pattern we are watching unfold this spring. The overload in the plains and Midwest, the suppression in the Southeast, the coordinated rhythm of intense outbreaks, all of it existed on paper years before it materialized on radar. This provides a remarkable validation of climate science. It is also a profound reminder that when researchers tell us something will happen under specific conditions, and then those conditions arrive and the event occurs on schedule, we should perhaps listen more closely. It suggests we should treat these scientists not as background noise, but as the forward observers they truly are, providing invaluable foresight. When we pull back to survey the entire picture, we see ENSO shaping the geography of severe weather this spring. We see jet stream configurations enforcing the cadence of the outbreaks, and a broader climate baseline that has, over decades, increased the available ingredients for severe weather in general. These three factors, working in concert, are producing the 2026 season we are currently experiencing. None of this is random, and none of it is unpredictable in the ways that truly matter. The pattern has a structure, and that structure is knowable. This knowledge is also actionable, which is why it is so important. When you understand the structure, you can prepare for it. Without that understanding, every outbreak feels like a new shock, and every shock represents a missed opportunity to have been ready. This pattern shows no signs of ending. The Pacific continues its trend toward El Nino, and the jet stream remains locked in its current configuration. Troughs are still ejecting on schedule, and the atmospheric reloads are still coming. Each iteration of this pattern builds upon the last, and the force that sustains it is not weakening. If anything, that force is strengthening, suggesting the pattern may evolve into an even more pronounced expression in the weeks and months to come. The ground across the Midwest is already saturated, the air masses are loaded, and the jet stream is firmly in place. Each new reload arrives with a slight head start over the one before it, an accumulation that helps explain why this season feels so relentless to those living within the overloaded zone. And this leads us to the question that has been hanging over this entire analysis. What happens when El Nino fully arrives? What will occur when the preliminary El Nino signal we have been watching becomes a fully developed event, and the atmospheric response scales up accordingly? What will it look like when the rulebook is read from its full-strength chapter, rather than its prologue? These are the questions that the spring and summer of 2026 are poised to answer. The answers will shape our understanding of severe weather in a changing climate for years to come. They will not be found in academic papers, but in tornado reports, radar loops, outlook maps, and unfortunately, in damage assessments. These answers will arrive whether we are ready for them or not. The only variable we truly control is how seriously we choose to take this preview we are already living through. If there is one thing to take away from all this, It is that the atmosphere is not behaving unpredictably this spring. It is behaving exactly as expected, given the conditions in the Pacific Ocean. The fact that it is following a script, one written in a research journal over a decade ago, is not comforting. It is the warning. When the atmosphere adheres to a script this cleanly, it tells you that the forcing is strong, the pattern is stable, and the trajectory is toward more of the same, not less. In this context, predictability is not a comfort, it is the alarm. We are not in a chaotic season. We are in a structured one. And structured seasons, especially when driven by a climate signal that is still building, do not simply moderate on their own. They continue. They intensify. They write their next chapters in the same handwriting as the ones before. April 17th was one such chapter, and April 23rd is the next. The chapters that follow will be written in the coming weeks and months, and they are part of a book whose outline we have already read. Published at a time when no one knew this particular spring was coming. This is what makes this moment so unusual. We typically analyze the weather after it has happened. This spring, we have the rare and sobering experience of watching weather that was described before it occurred, unfolding in the precise sequence the description predicted. The storms that have torn across Wisconsin, Kansas, and Oklahoma this April are not the work of an angry or random system. They are the work of an atmosphere doing exactly what physics and climate science say it should do under the conditions currently in place. And that is the most sobering realization of all, because it means the pattern will persist as long as the conditions persist. And those conditions are only moving further in the direction that drives this pattern. There is no external force coming to break this cycle. The cycle will break only when the Pacific tells it to. The Pacific Ocean is not acting as a moderating force. Its influence is one of amplification. So in the coming weeks, when you witness a tornado warning illuminate the map of the central United States, or see a compound event where hazards from different seasons converge on a single day, it is crucial to see the connection. Even the unusual quiet over the southeast, when compared to its typical activity, is part of this same story. Nothing about this is arbitrary. It is all unfolding within a discernible structure, and this very structure is the warning. It is the framework that distinguishes this season from any ordinary one, telling us that what follows will not mirror the patterns we have known before. For the informed observer, understanding this underlying architecture offers a profound advantage over someone merely watching storm coverage on the evening news. If you reside in the plains or the Midwest, it is essential to treat every warning this season with the utmost seriousness. The atmospheric system generating these outbreaks is not a singular event. It is a persistent engine that will continue to ignite. For those in the southeast experiencing a period of relative calm, it would be a mistake to interpret this quiet as long-term safety. The ENSO signal, which is currently redirecting energy away from your region, will inevitably shift, and when it does, the storms are destined to return. And if you are watching this unfold from anywhere else, consider this season a compelling case study. You are seeing a textbook example of how a dominant climate signal can seize control of an entire continent's weather, refusing to relinquish its grip. What we are witnessing this year is not an atmosphere behaving erratically. On the contrary, it is performing with remarkable predictability, following a script authored by powerful natural forces. When a system of this magnitude, power, and consequence begins to behave exactly as anticipated, but in a direction pointing toward greater severity, the conversation changes. We no longer ask whether to take the threat seriously. We begin to ask how we must prepare for what is yet to come. This narrative is far from over. The Pacific continues its warming trend, the jet stream continues to pulse with energy, and the next chapter is being written above our heads in real time. This unfolding chapter is inscribed in the language of science, in sea surface temperatures, in anomalies within Kelvin waves, in the vast heat content below the ocean's surface, and in the shifting amplitudes of the jet stream. It is written in the slow, inexorable advance of an oceanic signal that has been building for months, showing no signs of abating. When this next phase arrives, it will be those who understood the preceding chapters who will have seen it coming. Those who dismissed this spring's activity as mere normal variability, or convinced themselves that a day like April 17th was an isolated fluke, will be the ones caught unprepared. Herein lies the profound difference that pattern recognition makes, and it reveals the true value of climate science when it functions as intended. This is why the quiet southeast holds as much significance as the turbulent Midwest, and why a 6 to 8 day cadence is as telling as 54 tornado reports. The subtle details are communicating a story that the headlines cannot. Therefore, remain observant, remain aware, and stay grounded in the science. In the face of such complexity, science offers the only reliable lens through which we can make sense of a sky that seems poised to give us ever more reasons to look up. Watch the meteorological outlooks. Watch the Pacific. Watch the southeast with the same diligence you watch the plains. And when the next outbreak arrives, right on schedule, remember that you are not seeing weather misbehaving. You are seeing it behave precisely as predicted, and an atmosphere that is trending in a predictable direction, especially the direction this one is trending, is the single most important signal to keep in your sights for all that is to come.